As a musician, I often want to recreate guitar effects that I hear on recordings from my favorite bands. However, finding the right effects and parameters to use is not always easy. I would love to have a tool which can take an audio input and tell me which effects I need to use and how I should set their various parameters. This project is an attempt to use deep learning to achieve a simplified version of this tool. I will be attempting to estimate two different parameters simultaneously: the reverberance parameter of a reverb effect and the decay parameter of an echo effect. Each of these can take on a value from 0 to 1. If this project achieves its goal, it will open the door for expanding the project to handle a wider variety of effects and types of audio data. I have recorded 40 minutes of clean electric guitar to be used as my dataset. This recording includes a variety of playing styles from strumming, fast picking, harmonics, finger picking, etc. Much of it is structureless, dissonant, and quite frankly, ugly. And I did this in order to provide the greatest variety of information and avoid the repetition that comes with playing actual songs. For training my model, I will fetch random 3-second clips and apply a random amount of reverberance and echo delay to each clip. These randomly generated parameter values will be used as my training labels. 70% of the data will be used for training and 15% for validation and testing. When applying deep learning to audio, MEL spectrograms are commonly used. A spectrogram is a visual representation of an audio clip with time on the horizontal axis, frequency on the vertical axis, and amplitude represented by pixel intensity. I will be using two different convolutional neural network architectures in an attempt to infer the echo and reverb settings using the spectrogram images. The first model architecture will have a single branch with two different linear outputs to estimate each parameter's value. The second model architecture will have two independent branches which are dedicated to reverb and echo respectively. I will evaluate the models using mean squared error and will be comparing these against the benchmark score which a naive model would achieve. I completed this project in Google Colab, which gives me access to the powerful GPUs that are important for deep learning. I start by installing SOX, aka Sound Exchange, which is a tool for audio manipulation. I also install the PySoundEffects library, which is a Python wrapper for SOX. This is how I will apply the echo and reverb to sound clips programmatically. I then install the relevant libraries and define utility functions for applying audio effects to sound clips and for constructing and displaying spectrograms. One of the core pieces of this project is a custom data generator that I have built. Data generators provide a way to continuously generate and augment data without the need for holding all of the records in memory or even saving to disk. In my case, I will be grabbing 3-second clips with random start times and applying a random amount of reverb and echo to each clip on the fly. This ensures that no two training records will be exactly the same. Saving a comparable amount of training data to disk would take a huge amount of space, so the custom data generator really comes in handy here. Before getting in the weeds, I give the audience an opportunity to hear the echo and reverb effects for themselves. Let's start with no effects. Now let's max out the echo but keep the reverb at 0. Let's try max reverb and no echo. Finally, let's do some reverb and echo together. Okay, great. You can probably pick out the differences pretty easily, and you may have also noticed the shape of the sound wave changing as well. Hopefully, a machine learning model will notice it too. When working with audio data, machine learning engineers use a variety of tools. For cases like speech-to-text, RNN or LSTM-based models are common since information early in the input could provide clues about what to expect later on. For cases like sound classification, spectrograms are more commonly used. I chose to work with spectrograms since these effects are relatively local in time and due to the fact that the sound frequency profile becomes more important than temporal properties for effects such as pitch modulators. In these visualizations, we see the spectrogram of the original clip compared to those with max echo and/or reverb. In the case of max echo, we can sort of see a duplicate of the original shape shifted a bit to the right. We can look at this pair of peaks, or these two over here. In the case of max reverb, we see that the sound has been smeared out since the sound smoothly decays. In the case of max reverb and echo, we see both of these properties combined. Remember, the goal is not to simply predict whether echo or reverb have been applied, we want to predict the exact parameter values. It's important that the specific level of echo and reverb are deducible from the spectrograms. Here's what varying levels of echo alone look like. We do see that the echo becomes more prominent as the parameter increases, but distinguishing point 1 from point 2 is difficult. However, I had a hard time doing this by listening as well. All of the above applies to the reverb spectrograms as well. I now split my dataset and define callbacks for saving the best model and logging training stats. I start with a single branched model. I use two distinct linear outputs so that I can track the loss for echo and reverb independently. I train this model for 70 epochs. Before evaluation, I calculate a benchmark performance based on a naive model which would always predict the expectation values. We see a healthy decrease in loss throughout the training for all three graphs. We are well below the benchmark on each. We do see that the echo loss declined more rapidly and ultimately reached a lower value than the reverb loss. The reverb loss appears to decrease roughly linearly and then appears to ultimately flatten out in the last few epochs. We see some turbulence, which is likely a result of the small number of steps per epoch. I will now evaluate the model on the testing data. This model scored a total loss significantly lower than the benchmark value. Typical guitar amplifier effects contain dials that range from 1 to 10. With the MAE recorded above, this would mean that the predicted echo value would be off by less than 1 notch on average, whereas the reverb would be off by 1.6 notches, which is pretty good. Now let's collect and inspect some of the best and worst predictions on this testing set. Let's start with the clips with the highest loss. All three clips with the highest loss involve a big overestimation of the echo. The first two clips involve fast guitar picking. I suspect that these fast consecutive notes were mistaken as echoes due to the similar time scale. Now let's look at those with the lowest loss. Each of these clips have mid-range parameters and contain distinct notes which do not blend in or overlap with one another. This isolation likely made it easier to identify the relevant patterns. Instead of looking at individual clips, let's see how our loss varies across the range of actual echo and reverb. This heat map was created using averages of 5,000 predictions with effect parameters grouped in bins of 0.1. Interestingly, there appears to be two clusters where the model performed best. Mid-range echo with reverb around 0.2, and mid-range echo with reverb around 0.8. It's understandable why the area of best performance is roughly at 0.5 echo, since that is the safe prediction that a naive model would make, but I don't understand why there are two clusters. Perhaps the model became good at telling whether or not significant reverb had been applied, but not very good at estimating its precise value. This may be worth further investigation in the future. Now, let's try a second model architecture, which has a dedicated branch for each output. This time, I trained for 110 epochs since performance was still improving after 70. Again, we see a healthy decrease in all three graphs, but the echo and reverb loss reached a lower value than that achieved by the previous model. I do notice that the validation curves are a bit more turbulent than the previous model. This could be due to the state of the optimizer resetting upon continuing training after interruptions. Looking at the evaluation metrics, Model 2 has surpassed Model 1 by a significant margin. The predicted reverb would be off by 1.3 notches on an amplifier, whereas the echo would be off by less than 1 notch. I will not play all of the top scoring sound clips, but this clip with the second lowest loss is interesting. This clip is the same fast picking section for which Model 1 really struggled with. A quick test of setting echo to 0 suggested that this model is no longer mistaking the fast picking for echo. When looking at the average loss versus parameter values, we see the same two-cluster pattern, which continues to baffle me. I then tested my model on a very different type of audio data, spoken word. I used the audio from a Radiohead interview available on YouTube. The model performed pretty well when it came to reverb, but exceeded the benchmark loss for echo. This suggests that the model's echo recognition is less generalizable than for reverb, which may have been prevented with a more varied dataset. Overall, both models did very well at predicting these two parameters on guitar data, but there are a number of ways in which I can expand this project to be more general. As mentioned, a more varied dataset would help. Such data is readily available, but I would have to take measures to make sure I avoid sound clips which already have echo or reverb applied to them, or certain digital instruments which have reverb or echo-like properties built in. I would definitely want to expand the space of audio effects and parameters predicted by the model. As I do this, architecture becomes very important for scalability. It would not be sustainable to add a dedicated branch for every parameter we wish to predict. One option would be to have a separate branch for each effect, but have the output of each branch be a vector containing values for all parameters associated with that effect. Better yet would be something like an initial model responsible for simply detecting the presence of each effect. If an effect is detected, the input will be passed to a more specialized model responsible for predicting each of its relevant parameters. This would be the most maintainable solution since it allows us to introduce new effects with minimal retraining. It also allows us to bypass a lot of the computation if we can decide early on that a particular effect is not present in the sound clip. Lastly, not many musicians are using the SOX tool for making music. I would want my project to have value for musicians using popular tools like GarageBand and Logic. If these services don't offer the necessary APIs, then a second option is to work on building a mapping from the parameters our model was trained on to the equivalent parameters of the GarageBand or Logic sound effects. For example, I would need to find how to represent a 0.7 decay parameter in Pi sound effects using the parameters of the delay pedal from the GarageBand's pedalboard plugin. A user of my tool would only see the GarageBand converted values of the predicted parameters. Well, I hope you enjoyed this project as much as I did. Having never worked on custom data generators, multi-branch models, or spectrograms, I learned a lot while doing this. The success of this POC has really inspired me, and I really hope to find the time to begin expanding this project to handle more general audio data and a wider variety of effect parameters. Thank you for watching.